Also like crazy bits.
All right, so you'll need a calculator just for us to do a little bit of kind of glancing at the calculator to kind of remind us what's going on with the graph. So we'll use it minimally. We really won't need to use it very much for your homework. We're not really graphing today. We're going to find out the parts of the rational function. We won't be graphing the rational function per se. So rational functions are fractions. All chapter we've been working with polynomials. So they have powers, whole number powers. A rational function is really taking one polynomial and dividing it by a second polynomial. So you see that p of x divided by q of x. P and q are associated with rational functions. So anything that's a fraction usually uses the variables p and q. So it says p and q are polynomials. So one polynomial divided by a second. Q of x cannot be 0, because if it were 0, then it would be undefined and it wouldn't be a function. And then it also says that p of x and q of x have no common factors. Because if they had something in common and you could cancel out the q term, then again it wouldn't be rational. So they don't have anything in common. Just a little review, going back pretty much from the beginning of the year. How do you find domain without graphing? Just by using the equation. How do we calculate domain? What do you have to think about, Jesse?
If there's a denominator, it can't equal 0, and if there's a square root or like a Newman radical, whatever number it has to be like equal to 0, or greater than or equal to 0.
Exactly. So if you have a denominator, the denominator cannot equal 0. If you have a square root, the square root has to be greater than or equal to 0. So see if you can find the domain of the two equations, functions that are on there, just by looking at the denominator, asking yourself exactly what Jesse just kind of stated. So the denominator, if it has anything in the denominator, it cannot be 0. So Jesse, in the first case, x cannot be
Positive or negative.
right. So x cannot be positive or negative 1, because a 1 minus 1 would be 0, or negative 1 squared minus 1 would be 0. How do you write that then as domain, Jesse?
Negative infinity to negative 1 in parentheses, negative 1 to positive 1 in parentheses, and then 1 to positive infinity.
Nice. So when we say it cannot be a value, that's when we use parentheses. And essentially it's just hopping over that number, moving past it up to the next number, hopping over that, moving past it, and then going beyond. So because the x squared minus 1 in the denominator, x cannot be plus or minus 1. How about the second one? What can't x be in letter B? Okay? 2. So even though that's cubed, that's really saying you just have 3 of that same term. So whether you look at them as having 3 separate values, or is it just being cubed, there's only one number that's going to make that 0, because each one of those factors are exactly the same. So x cannot be 2. So Ben, that would look like?
It would be negative infinity to 2 in parentheses and 2 to
Good. And then 2 through infinity. Questions? So just to kind of go over what happens with a graph and why the domain is a specific part of the graph. It wants you to graph y equals 1 over x. So in your calculator, graph y equals 1 over x. If you know what it looks like, you might not have to graph it. Sketch yourself a little graph of 1 over x. You already know what it looks like. Graph yourself 1 over x.
I bet Emerson knows what the difference is.
Emerson's going to create a T-chart graph exactly.
So when you graph it, how many pieces of the graph are there? 2. So you should have 2 parts to the graph. One is in which quadrant? What quadrants are they located? 3 and 1? and they pretty much should skim along the x and the y axes. It's this curve, something similar to this. So it skims along the axes. Should have two curves that are diagonal from each other, symmetrical from each other. And then it asks for the domain. So we just said that x cannot be 0. So in this case, x would be from negative infinity to 0, and then 0 to infinity. So it says note the behavior around x equals 0. So underneath, it has two little things to think about. And we'll talk about this kind of throughout the year, but this notation, as x, that little arrow means approaches. We've used that before. And then the 0 has a little minus sign after it. And that little minus sign really means 0 from the left. Every number has a left or a right side. So it depends on which side of the number you're looking for or looking at to help us kind of answer different questions. So as x approaches 0 to the left, what does y do? Right.
Decreases.
So as x approaches 0 from the left, we're on the left side of 0, he's saying y decreases. What does y do? Like if it decreases, it goes to what?
It goes
What number is it going to?
negative infinity.
Negative infinity, yeah. So as we're getting closer and closer and closer to 0 for the x value, the y is going down to negative infinity. And then the other part says as 0 approaches, or as x approaches 0 from the right, that's what the plus sign after it means. What does y do? So now we're on the right side and we're just going in towards 0. Right, what does y do?
Increases to positive infinity.
Yeah, y increases to positive infinity. So a 0 has a left and a right side, and depending on which side of 0 you're looking at, the graph does a different thing. So on the left side of the 0, the graph goes down, but on the right side of 0, the graph goes up. Underneath, it gives you the definition of an asymptote. A vertical asymptote is defined by saying the line x equals a, so x equals 0, x equals 1, x equals 2, is a vertical asymptote if y goes to infinity or y goes to negative infinity. If you prefer to think of that as y, that's fine, but f of x and y are the same thing. So an asymptote exists when the y values of the graph go to positive infinity or negative infinity, as our x goes to a specific number from the left or the right side. That's the actual definition of an asymptote. Yes, it's when the denominator is undefined, but graphically it's when the y is going up and down, like when the graph is splitting. So the y value is going up to infinity, going down to negative infinity. That's the true definition of an asymptote. We write an asymptote in x equals 4. So the asymptote here would be at x equals 0. That's where our asymptote would be located. So see if you can, there we go, figure out what the vertical asymptote would be for the next example. In a sense, we're setting the denominator equal to 0 instead of not equal to 0 because now we want to know where that asymptote is. So it can't be this number, that's where your asymptote really exists. So grant the vertical asymptote for 1 over x minus 3 is?
X equals 3.
X equals 3. So that's where our asymptote would be. That asymptote then creates the domain as well, because it still can't be that number. That's what an asymptote says. It's still not allowed to be that number, but now we have this line in the graph. Questions? So vertical asymptote is found by setting the denominator equal to 0 and solving for the value that still x cannot be that value, which creates our vertical asymptote. So there's another type of asymptote, and that's the horizontal asymptote. So it says pretty much the opposite. The line y equals b. So now horizontal is a y equals line. Is a horizontal asymptote if f of x approaches b, which means as y goes to this number, x must go to infinity or x must go to negative infinity. Same exact definition as a vertical asymptote, but now we're going to see that the x is going to go in a different direction. So looking at this graph, you don't have to flip back over, but if we're going to 0 from the top and the bottom, notice the graph is spreading. The x values are going to positive infinity and negative infinity. That's the definition of an asymptote. So when your graph goes to positive infinity versus negative infinity, an asymptote exists. Whether it's a vertical asymptote or a horizontal asymptote, it just kind of depends on what direction of the graph you're looking. Can a graph ever pass a vertical asymptote? Can it cross over or touch a vertical asymptote? No. So a graph never crosses a vertical asymptote. Because that's where it's undefined. That's the number it cannot be. But a graph can cross over a horizontal asymptote. Because we don't find it by saying what is the denominator when it's undefined. That's not how we find a vertical asymptote or a horizontal asymptote. So for a horizontal asymptote, it really is looking at the graph and saying, is the graph going to infinity or negative infinity? It's allowed to cross it. We'll see that there are times that it'll cross it in the middle of the graph, but it's the ends of the graph looking at the x value. Is it x going to infinity or negative infinity? So the example here, I want you to graph this on your calculator. And just take a look at what the horizontal and the vertical asymptote are. Greg, you have it
I
done?
just know what they are.
So horizontal is the vertical is the x equals, horizontal is the y equals. Your vertical asymptote we know how to find by setting the denominator go to 0. The horizontal one, see if you can use your table of values, just look to see what number the graph is approaching. So Jacob, what do you have for the vertical asymptote? -1. So if we set that equal to 0, that's where our vertical asymptote is. And the horizontal asymptote, where's that one? Greg?
It'd be 2.
It's at 2. So again, if you're not sure, trace it. Go to the table of values. See what's going on with those values. Are they getting closer and closer and closer to a number? That's when you know there's a horizontal asymptote. They should be decimal values getting closer and closer to 2. So we're going to review the 3 little shortcuts for horizontal asymptote. So a horizontal asymptote is not when the denominator is undefined. That's a vertical asymptote. So it's not really when your function is undefined that we're looking for. It's just different things happen with the function to create that asymptote. It's the y values of the graph. So the first rule says if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the coefficients. We talked about these 3 rules last year. So this is kind of just a refresher to kind of go over why horizontal asymptotes exist, what to look for in the graph. So if we had, we'll say 3x squared plus 1, 4x squared minus 1. Whatever, it doesn't matter. If the degree of the numerator and the denominator are the same, so we're looking at the powers. If those powers are the same, then where is the asymptote? Where would this asymptote be located? Elena, what do you think? At 3/4. So it's the coefficients in front. It's in y equals form. It would be y equals 3/4. Powers are the same, it's the coefficients in front. And you're looking at the largest power. So if there's multiple powers there, you're comparing the largest power on the top, the largest power on the bottom. And you can check that in your calculator if you're looking at the y values.
So we just ignore the rest of that.
Ignore the rest of the numbers. So it's only the coefficients in front of those largest powers. The largest powers define your graph. Even with polynomials, it was that first power that defines what the graph looks like, so you ignore the rest of it. The second shortcut rule says if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at 0. So if I take that same equation, but change it to 3x plus 1 and 4x squared minus 1. So we're looking at the power of the top versus the power of the bottom. The rest of it doesn't matter. So it's just those largest powers that we're looking at. So the top power has a smaller number than the bottom power. As we're looking at a first versus the second. So then this horizontal asymptote is at y equals 0. No matter what. As long as the power on the top is smaller than the power of the bottom. And then the last one says if the power on the top is bigger than the power on the bottom, then the horizontal asymptote does not exist. There isn't a horizontal asymptote. So taking the same equation that we were working with, 3x squared plus 1, and then maybe on the bottom we only have 4x minus 1. So looking at the largest power of the numerator and the denominator, so this time the degree of the numerator is greater than the degree of the denominator. So you would just say that the horizontal asymptote does not exist. And you can just use D and E. It's not there. There's nothing that's going to stop the graph horizontally. There is still an asymptote there, but it's not a horizontal one. Questions? So we're going to just see if we can kind of work through a couple of problems. Just looking at the pieces of the graph, trying to figure out if you have a function, what part of that function creates different parts of graphs. Now we're looking at rationals, so fractions. So if you look, I tried to organize it fairly neatly, but we have a function. Underneath, we're going to try and figure out the vertical asymptote, the horizontal asymptote, the domain and range, and then the x and y intercepts, and then if there is any symmetry. So we have f of x equals 1 minus 5x over 1 plus 2x. And I want to see if we can do as most of this as possible without relying on the calculator. So what piece of the equation would you use to find a vertical asymptote? The denominator. So we're going to take the denominator, set it equal to 0. So the denominator is where the vertical asymptote is found. And then if you set that equal to 0 and solve, Emily, what do you get? Negative 1/2. So there's a vertical asymptote at negative 1/2 because that's where the x would be a 0. It gives us a 0 in the denominator. That number is not defined. The second part, a horizontal asymptote. So looking at this question, Emma, how do we know if there's a horizontal asymptote?
Look at the powers.
And if you look at those powers, what would you say about them?
They're the same.
Yeah.
So you have to use the coefficients.
So the power of the top is the same as the power of the bottom. So she said you need to use the coefficients, and those coefficients will be what, Emma?
Negative 5 pounds.
Yeah, so negative 5 on the top and the 2 on the bottom. Which asymptote gives us the domain of a graph? Abby. Yeah, the vertical asymptote describes the domain. It helps you create the domain. So Abby, this domain would be
Negative infinity to negative.
they will always go together. The vertical asymptote creates the domain. Because those are the numbers that it cannot be. So that means those numbers need to be listed in your domain. I'm going to skip the range for a moment. We'll come back to it. How would you find an x-intercept? So how do we find x-intercepts of graphs? What do we do to get an x-intercept, Ben?
Set x equal to 0. Y.
Y, yeah. So we want to set y equal to 0. And then if we're finding a y-intercept, you would
Set x equals.
set x equal to 0. There we go. Okay, so for the x-intercept, we have 1 minus 5x, 1 plus 2x. Setting it equal to 0, exactly what Ben just told me. Ben, how would you solve for x?
Well, you'd have to take part of it to the other side, so
Right.
that the x would be by itself.
So you would need to take whatever's in the denominator to the other side. So if you multiply that denominator to the other side, Ben, what happens?
Then you have an x value and a numeric value on both sides, so you can just subtract 2x from both sides and a 1 from both sides, and it's going to end up being
Hold on, Ben. If you have a 0,
What?
because you said you were supposed to make y
Oh,
0, what is 1 plus 2x times 0?
0.
0. So if you take that 1 plus 2x to the other side and multiply it by 0, it's still 0. So your x-intercept is found by setting the numerator equal to 0. The denominator finds the vertical asymptote. The numerator finds our x-intercepts. So Ben, if we set the numerator equal to 0 and solve, you would get
You would get 1/5.
1/5. So our x-intercept occurs at 1/5 and 0. So it's really setting the numerator equal to 0. The denominator forms the vertical asymptote. It has nothing to do with the x-intercepts because you're multiplying that to the other side and it's still 0. And then the y-intercept, Ben said to take all the x's and let them equal 0. So we would have 1 times 5 minus 0, 1 plus 2 times 0, which really equals 1. So that would be a 0 and a 1. The last two questions that I skipped over, you will want to look at the graph to get the range, because not all times will the range completely coincide with the horizontal asymptote. Sometimes it does, sometimes it doesn't. And then symmetry, there are 3 types of symmetry. You could have symmetry about the x-axis, which really means it's not a function. You can have symmetry about the y-axis, and you can have original symmetry. Those are the only 3 types of symmetry. Don't say that it has symmetry about x equals 2. So it either has y-axis symmetry, x-axis symmetry, or original symmetry. So when you look at the graph, if it's not symmetrical about any of those, then it doesn't have symmetry. So look at the graph to get the range. Look at the graph to see if there's symmetry. So this range goes from negative infinity to what? Jesse?
Just
Make sure you put parentheses around the numerator and denominator. Did you do that? For letter A? That line is your asymptote. That's your vertical asymptote. So like looking at these 2 lines, what are they? So you're looking at the lines that are going horizontally, that are going to negative infinity, positive infinity, and is spreading out horizontally. Should be negative 5/2 and positive negative 5/2 to positive infinity. So if you trace those lines, trace them out as x is getting big, as x is getting smaller. And then this graph has no symmetry. It's not symmetrical about the x-axis, it's not symmetrical about the y-axis, it's not symmetrical about the original. Questions? Alright, so let's see, which one is it? Let's look at letter C, just going underneath. So vertical asymptote is when you take the denominator, set it equal to 0. What happens when you set this denominator equal to 0? Emily? Yeah, you get an imaginary number because you're taking the square root of -1, which is really plus or minus I. So Emily, what do you think that says about a vertical asymptote? There isn't one.
Or there is, it's just too good to be real.
It's just imaginary. So technically, in our real number graph, there is not a value that would make the denominator 0. So there isn't a vertical asymptote. How about the horizontal asymptote? Which rule is going along with the horizontal asymptote? Right?
So you said y it'd be 4 because you said the numerator equal.
What?
Okay.
How about the power of the numerator?
I'm
versus-
sorry.
No, you're right.
It's smaller.
So the power on the top is smaller than the power on the bottom. So that means the horizontal one is at y equals?
0, right?
Yeah. So horizontal asymptote, y equals 0. Because the power on the top is smaller than the one on the bottom. There isn't an x on the top. So the power of that x would have to be smaller than the one on the bottom. The domain, if there is not a vertical asymptote, your domain is negative infinity to positive infinity. Because there's not a number that's breaking up those x values. We'll skip the range so you can look at that in the graph. The intercepts would be when you take the numerator and set it equal to 0. Gray, maybe you were giving me this one?
Yeah, it was.
What happens when 0 is equal to 4? 0 does not equal 4, so that means there are not any x-intercepts. And then the y-intercepts, we would have 4, and then what is it, 0 squared plus 1? Which is 4 over 1, so we have a y-intercept at 0, 4. So graph this, put it in your calculator, see what the domain, or I'm sorry, see what the range is, and see if there's any symmetry. Anybody graph it already? Emerson, what kind of graph does it look like?
It's like an upside down V, but not quite. So
Yeah, but it's curvy.
There's a hump.
There's a, yeah, like there's a mound in the middle. Let me draw a nicer one. Something like this.
yeah, there's like a, it's like sharp at the top.
Sharper at the top. So that top point, Emerson, do you know what that top point is?
0.
That top point is your y-intercept at 0, 4. So your range, Emerson, would be from,
It would be from 0 to 4.
and what goes around the 0?
The 0 is a parenthesis, 4 is a bracket.
The 0 is a parenthesis because that's where you have an asymptote. The 4 is a bracket because that's the top part of that mound, which Emerson says a little sharper than what I have drawn up here. Emerson, is there any symmetry?
There is x-axis.
So close.
Sorry,
I think, nope, you're good. I think you meant y-axis. Y-axis symmetry.
Instead of 0, it would be
Questions? So when you're working through all these pieces, the vertical asymptote is the denominator. Horizontal asymptote, look at your powers. X-intercept is the numerator. The y-intercept is changing all the x's to 0. So those are like the 4 key things that you need to think about when you're interpreting a graph. Tonight's homework is on the assignment sheet. It's on page 147. Please make sure you've got like a little bit of work supporting your solutions. You shouldn't really have to do much graphing. It's more kind of analyzing and interpreting the graphs. Have a great day.